Hi everyone and welcome to this next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In today's lecture we are going to look at an analytically trained example of a simple decision tree so as to solidify the concepts that I have been looking at in the last few lectures. And although most of the things in machine learning happen numerically on a computer, it does have some benefit to look at how exactly this happens in the background so that we can develop some intuition into the machine learning models. So let us go ahead and get started with this example problem. So the example that we want to do pertains to a simple decision tree . And what we wish to do here is we want to develop a single node decision tree, which is also called a decision stump, to predict whether a given material is a good photoelectrocatalyst for water splitting. So water splitting is a procedure used to produce green hydrogen, and then we want to find whether a given material is a good photoelectrocatalyst or not. We want to train decision tree, and to keep things simple analytically solvable, we are only going to look at a decision stump, which is essentially just one node of a decision tree, and we are going to see how this works. Okay. So now as there is some data that has been given for this particular problem. This is of course data that we have created for this problem, but there is some element of truth to all of this data, right. The features that we have taken, these are all categorical features, and mostly these are just yes or no type features. So we are going to look at the band gap of the material, whether it is capable of absorbing light or not, right. So whether the band gap is greater than 2 electron volts, this is a feature. We are going to look at whether it is an n type semiconductor or not. So for each of these features I am putting a question mark after this, that just means it is a yes or no type of a categorical feature. Then the cost of any thing in engineering is very important. You can't deploy solutions that have huge cost. So we are going to look at whether the cost is greater than, let us say, $1000 per kilogram, that is a feature. Then we are going to look at what is the potential required for splitting water. So that is something called over potential, and we are going to ask if it is less than 1 volt or not. Lesser the over potential better. So we are going to see whether it is less than 1 volt, 0.5 volt, and then we are also going to see whether the over potential is less than 1 volt. And finally we wish to predict whether the material is a good or a bad photoelectrocatalyst. Okay. So this is the data set that we have been given. These are the features. So as you can see, there are how many features? So there is band gap, whether it is n type or not, cost, over potential, and whether the over potential is less than 1 volt. So there are 5 features for every material, and there is one target variable y hat that we want to predict, and of course these are the true values here. So we are writing y here. Okay. So this is the table that we are trying to create, and based on this table we want to train our machine learning model. Okay. So let us go ahead and start populating the data that has been given to us in this data set. Okay. So, the first material that has been told to us is known as nickel oxyhydroxide, NiOOH. So, for those of you who are a little far away from chemistry, it is okay, you can just call these materials as A, B, C, D and so on, and it will not make a difference to you. So, this does not have a band gap greater than 2 eV, this is an N type material, the cost is not greater than 1000, the over potential is less than 0.5, it is also less than 1 of course, right, and then it is a good photoelectrocatalyst, that is what has been told to us. So, this is data that is available to us. Then we are looking at something known as titanium oxide, TiO2, this is has a band gap greater than 2, is an N type semiconductor, cost is low, over potential is not less than 0.5, but it is less than 1 and it is a good photoelectrocatalyst as well. The next one is called BiVO4, bismuth vanadate, again the band gap is greater than 2, so it can absorb light, it is not N type, its cost is greater than 1000, over potential is not less than 0.5, it is less than 1 eV though, but it is a bad photoelectrocatalyst, right. This is of course subjective whether it is good or bad, this you can just think of it as data that has been given to you and it may or may not be factually correct, right. So, I will just fill up the other entries in this table, it is a slightly long table, but hopefully it makes sense. So, yes, yes, no, no, yes, and then it is good, and then there are actually 6 more data points. So, I will complete the table here. So, this is yes, yes, no, yes, yes and good, and similarly you can add the other entries here. So, if you can see here there is so much data that we have collected right from various research papers. So, a good part of machine learning especially in the core engineering disciplines is also collecting data from the literature, right, because this data may not be in the format that is directly amenable to machine learning. So, it is up to the person developing the machine learning model to actually look at the data really carefully and then create a machine learning model out of it. Okay. So, that is something that you should keep in mind. So, this particular material is a really costly one. So, you can see that it is a bad photoelectrocatalyst. Of course, it also has certain other unfavorable features, it does not have a band gap and so on. This other material also, it has no, no, yes, yes, yes and bad. So, you can see that these two materials here, right, they have almost the same kind of features, right, basically identical set of features and identical set of target variable as well. So, already you can see some patterns that emerge in this data set. When you are looking at a data set, always good to look at these kind of patterns because they will tell you if you are on the right track or not. So, for this particular material MoO3 molytrioxide, it has a band gap and then it is an N type, right, but it is also cheap, but it is not having a low over potential. So, that is also bad, and then there is something called chromium oxide CrO2. So, here you have no, no, yes, no, no and it is a bad photocatalyst, and finally VO2 you have no, 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 no. So, all of these are no and then it is a bad photoelectrocatalyst. Okay. So, this is the data that we have been given here, and basis this data we have to train a machine learning model. Okay. So, you can see here that the data is fairly well distributed. There are 1, 2, 3, 4, right. There are 4 examples of good photoelectrocatalysts, and then there are 6, 1, 2, 3, 4, 5, 6 examples of bad photoelectrocatalysts. So, overall there are 4 good and 6 bad photoelectrocatalysts, and it is nice to have a good distribution of data in your training set to be able to make good predictions. Okay. Now if you remember how the training happens is, right, so and this is just for the head node, right, we are talking about the first node in the decision tree. So what we do is we need to find the best feature cut point combination. The good thing about categorical features though is that the cut point is only basically yes or no, the cut point is already predetermined, you can already only have two splits yes or no. It is not like you have a feature such as a voltage which can take any value between 0 and 10. So the cut point could be 3, which means that less than 3 you go to the left node and greater than equal to 3 you go to the right node. So for a continuous feature it is quite challenging to find the cut point, but because we have all categorical features you only have yes or no in each case. So the cut point is basically already known, we just have to find the best feature, yeah, and you know that we are working with 5 different features here, whether it has a band gap, the type of semiconductor, whether it is a low cost or sorry whether it is a high cost, whether the over potential is low or not, right. So basis that we have to predict whether the material is good or not. If you remember what we do is we try to find how much, if you select a particular feature, the impurity of the node comes down, right. So we use the feature that results in greatest reduction in the node impurity, okay. And if you recall we had discussed 2 measures of node impurity, one was called Gini impurity and this was defined for a particular node Rk as 1 minus some C going from 1 to D p hat kc squared, right, where there are d different classes, right. This refers to the total number of classes, C is the index over the classes. So this was Gini impurity and the other was basically the entropy as a measure of node impurity. So that was H as a function of Rk, and this entropy of course you are more familiar with is just minus P log P, right, sum over all the classes. So this is minus P hat kc log P hat kc, okay. And you also have some intuition already on how this entropy works, given that we have discussed so much about classification problems where the cross entropy is the loss function. You do have an intuition about the entropy, right, but what we have so far not developed is an intuition regarding the Gini entropy, right. Why exactly is it defined as 1 minus some P hat kc whole square. So let us spend a few minutes trying to understand the rationale behind this kind of a definition, okay. So first things first, the Gini impurity, it measures the probability of misclassification if we randomly assign class labels based on the class distribution. Okay, so how do we quantify this? So essentially the impurity measure G is sum over all the classes. So C going from 1 to D, there are a total of D classes, right, and you take the probability that the point is assigned to class C right, that is the probability with which you assigned a certain point to class C times the probability that the point does not actually belong to class C. Okay. So, this is some C going from 1 to D. The probability that the point is assigned to class C is basically P hat K C, because we are assigning classes based on the class distribution. So, we just take the probability, right, of the point being assigned to class C, and that is the probability that the point is assigned to class C, because we are doing all these assignments randomly. Okay, times the probability that the point does not belong to class C, that is simply 1 minus P hat K C. Okay. So, now if you simplify this further, this becomes sum over P hat K C minus P hat K C squared, right. I am just opening up the bracket here, and then you have some C going from 1 to D P hat K C minus some C going from 1 to D P hat K C whole squared. The nice thing now, of course, and you may have already noticed this, is that probabilities always sum up to 1. So, some C going from 1 to D, if you sum over all the classes, the probabilities, right, are obviously going to sum to 1. So, your Gini impurity becomes 1 minus some C going from 1 to D P hat K C squared, and this is exactly what we had written on the previous page, as well as several lectures ago when we were talking about the training of decision trees. So, I hope you now understand where at that time we had written that expression. The Gini impurity essentially measures the probability of misclassification if we randomly assign class labels based on the class distribution, right. This entropy, of course, you do have a much better understanding, because you have worked with classification models, binary classification models. So, what we will do in today's lecture is we will just use the Gini impurity to find out, right, which feature results in the greatest reduction in the Gini impurity, and then we will go ahead with that feature as the optimal feature for the parent node. Okay. So, one point I just want to mention before we go ahead is that if P hat K C is 0 or P hat K C is 1, you can see that your Gini impurity is 0. Why? Because there is only one class in the region. So, there is a lot of certainty. So, we should like those kind of regions. So, essentially there is only one class in that node. Okay. So, with 100% certainty we can know what that class is, and therefore, the impurity is 0, right, and this is why you want to minimize the impurity. You want to pick the feature that will lead to the greatest reduction in the entropy or the maximal gain in the information. Okay. So, let us go ahead and see how it is done for this particular case. Okay. So, what we need to do is we need to find the information gain and that is obtained as the impurity of the parent node minus the impurity of the child nodes, right. And why I am writing child nodes here? Because whenever you select a feature, due to the binary splitting nature, you will always have two child nodes. So, you will have to take a weighted impurity of the child nodes. So, this information gain is the impurity of the parent node minus the number of the fraction of points in the left region. So, you know that there will be a left region and a right region. So, the fraction of points in the left region NL divided by NL plus NR times the impurity of the left child node and then again minus the weighted impurity of the right child node. Okay. So, how will this happen in our case? Okay. So, for our case we have to find the probability of the parent node, sorry, the impurity of the parent node. So, let us take the parent node and then we look at what is the impurity of the parent node, right. So, we want to find the G of the parent node, which is essentially 1 minus some C equal to 1 to D p hat k c squared. Okay. So, let us go back and see our data. So, where is our data here? So, we have good, good, bad, good, good, and then bad, bad, good, bad, bad. Okay. So, I have this point needs to be corrected here, this is good. Okay. So, do keep that in mind. So, I should fix this here. There are 5 good points and then 5 bad points. Okay. So, it is an evenly split data set. So, the first 2 points are good and then the third is bad, 4th and 5th are good, 6th and 7th are bad, 8th is good and then the 9th and 10th are bad. Alright. So, there are 5 good and 5 bad points and this helps us find the impurity of the parent node, right. So, this is what is the impurity of the parent node. So, we need the p hat k c. Okay. So, C is basically either good or bad. There are only 2 classes. D is 2 because we are working with a binary classification problem. We have to say whether it is good or bad. So, then you can look at in this parent node. So, K is denoting the region. So, we are looking at the parent node, what is the probability of good, and we just saw that there are 5 out of 10 points, right, which are good. So, that is just 0.5 and then p hat of bad is also 0.5, right, whatever remains. Okay. So, I hope this makes sense. We can again go back and you can convince yourself that there are 5 entries that are good here and then 5 entries that are bad here. So, then for this particular parent node the p hat k good is 0.5 and then p hat k bad is 0.5. So, then the impurity becomes G of the parent node is just 1 minus 0.5 squared plus 0.5 squared. So, we have to add up p hat k good squared and then p hat k bad squared. Okay. So, this becomes 1 minus 2 times 0.25. So, this is just 1 minus 0.5 which is exactly equal to 0.5. So, that is the impurity measure, right, Gini impurity of the parent node. Okay. Now, we have to decide what feature has to be used the next. Okay. And by the way, you could have also computed the entropy of the parent node. I am just writing it so you can do this calculation on your own. Yeah, the parent node is also called the root node. Okay, and H is what is used for Shannon entropy, and here because there are only 2 classes I am going to use log to the base 2. So, this is p hat log of p hat, right. So, p of good plus p hat log p hat for the bad points. Okay. And this if you compute will come out to be exactly 1 because we have used log to the base 2 here. Of course, you can use log to any other base as well. Okay. Now, let us see what will happen if we split the tree by band gap. Okay. So what will happen if we do the split using this particular feature? So what will happen is, like I said, you will have partitioned the parent node. So this is the parent node into two regions, okay. So this is the left region and this is the right region, and this has been done based on whether the band gap is greater than 2 eV or not. You know that it can either be a yes or no answer based on this band gap greater than 2 electron volts, okay. So for this we want to look at the left region and the right region, right. So we do need these metrics, what is NL, what is NR, right, and what is the impurity of the left node, and then what is the impurity of the right node. So once we know all these metrics, we will be able to compute the information gain, and that will tell you, right, what is the gain with this particular feature, which is the band gap. Then you will have to repeat the calculation with a different feature, right, and then you have to compare what is the information gain between those features, and then you choose the feature which leads to the highest information gain, okay. So that is how we operate. So let us go ahead and focus on the left region, okay. So first things first, how many points are there in the left region? Let us try to find out. So that will give you NL. So left region means that the question band gap greater than 2 eV has to be answered by a yes, okay. So let us go back to the table. So band gap greater than 2 eV, how many points are saying yes, okay. So 1, 2, 3, 4 and 5. So that means that the left region has 5 points, and because the total number of points we are considering is 10, that means the right region also has 5 points, okay. So we can now write that NL equal to 5, and then you can just remember that NR is also equal to 5 because the total number of points is 10. So this is the left region. Now we have to find P hat Kc, right. So P hat, so this region is the yes region for the band gap. So I am going to write it as P hat yes slash good, right. So this, because this is P hat Kc, or if you want you can even add a comma because it is not a conditional probability. So P hat yes comma good. So we are trying to have P hat Kc. So K is yes for band gap greater than 2, and then C is good, right. So that is the class we are looking at. So this will be the number of yes comma good divided by the number of yes comma good plus the number of yes comma bad, right, because we are looking at the left region. So now if you go and count, you will have 4 yes comma good, and then you will have only 1 yes comma bad, and this should be 4/5. Let us go back and check. Do you have 4 yes comma good and then 1 yes comma bad? Okay. So out of these yeses which I have circled here, right, how many are good? Okay. So out of this yes, this is good, this yes is bad, this yes is also good, this yes is good, so 3, and then this yes is good. So you can see that out of the 5 yeses for band gap greater than 2 eV, 4 of them are good and only 1 is bad. So that is what I had written there on the previous page, that n of yes comma good is 4 for band gap greater than 2 eV, and then n of yes comma bad is just 1. So P hat yes good is 4/5, okay. And similarly P hat yes bad is just what remains, so that is just 1 divided by 5, so it is just 1/5. So now you can find the Gini impurity of the left node, which is 1 minus P hat Kc whole squared, 1 minus 4/5 squared minus 1/5 squared. So this is 1 minus 16 divided by 25 minus 1 divided by 25, so that is 1 minus 17 by 25, which is 8 divided by 25, and that is simply 0.32, Okay. So, this is what went into the left region. Now, the analysis has to be repeated for the right region. So, let us go ahead and do that. You can see how carefully this has to be done, and obviously on a computer you should be able to write code to be able to recursively do this. Many of these codes have already been written, but as I have stressed in many of the previous lectures, if you can write your own code then that means you really understand what is happening. So, if you go back, the right region is all about the band gap not being greater than 2 eV. So, we have to look at the points where your band gap feature says no, and then there are only two classes. So, you have to find p hat no good and then p hat no bad. Okay. So, out of the no, how many are good and how many are bad? Okay. So, which ones are the no? The no ones are here, let us circle them up. So, the no ones are 1, 2, 3, 4 and 5. So, out of the 5 no ones, okay, 1 is good, this one is bad, this one is also bad. So, so far out of the no's only 1 is good, and then out of the no's, yes, 1 is good, and then this no corresponds to a bad, this no also corresponds to bad, and then these 2 no's also correspond to bad. So, 4 of the 5 no's are corresponding to bad and only 1 of the no's is corresponding to good. Okay. So, this means that p hat no good is simply 1/5, 1 out of 5, and p hat no bad is simply 4/5. Okay. So, your Gini impurity of the right node is 1 minus 1/5 whole squared minus 4/5 whole squared, and this is also 0.32. Okay. So, now you get the weighted impurity, which is NL divided by NL plus NR times G of L plus NR divided by NL plus NR times G of R. So, you can put these numbers in, but if you remember, you had 5 nodes in the left region and 5 in the right region. So, this is just 5 divided by 10, G of L was 0.32 and G of R was also 0.32. So, this whole thing comes out to be 0.32. So, that is the G of the child nodes. Okay. So, now what is the information gain? The information gain Ig is simply the impurity of the parent node, which is 0.5 minus the weighted impurity of the child nodes, which is 0.32. So, the difference is 0.18. So, that is the information gain which you have achieved here. Okay. So, clearly, right, if you are splitting by your band gap as the feature, you do gain some information, okay, which is good. Now, let us look at a feature where you do not gain anything, and that can also happen, right, and I will quickly walk you through this example. So, instead of splitting by the band gap, if we had split by over potential less than 1 volt, what would happen is that the left and the right regions would be quite different. So, the left region, and you will have to compute p hat yes good and p hat yes bad here. So, if you look at over potential less than 1 volt, p hat yes good would be half. Okay. So, over potential less than 0.5. So, p hat yes good is there is one yes here and then 2 yes here, both of these yeses are corresponding to good, and then these 2 yeses are corresponding to bad entries here, right. So, you can see that for 2 yeses there are 2 goods, and then for 2 yeses there are 2 bads. Okay. So, you can see that p hat yes good is just 0.5. Okay, and yeah, just to clarify, this is not over potential less than 1, it is over potential less than 0.5 volts. So, p hat yes good is 2 divided by 4, that is half, and p hat yes bad is also 2 divided by 4, which is also 1 half. Okay. So, the impurity of the left node is 1 minus half squared minus half squared, and half squared is 0.25. So, that is just 0.5 total. Okay. Now, if you looked at the right region, and I am leaving this for you to see, right, there will be 6 points, right, in the right region, and out of these 3 will be good and 3 will be bad. So, for the right region you will again get the impurity to be 0.5, because there will be 3 good and 3 bad. Out of the no's for over potential less than 0.5 there will be 3 good and 3 bad. So, then when you find the weighted impurity of the child node, that will be 4 out of 10 points in the left region with 0.5 plus 6 out of 10 points in the right region with also an impurity 0.5. So, this is again 0.5. So, what is the information gain? Information gain was the impurity of the parent minus the weighted impurity of the child. So, this was 0.5 and this is also 0.5. So, if you actually used over potential less than 0.5 as a feature, you would not gain any information. So, clearly it is a suboptimal feature, and out of the 2 features that we discussed, over potential less than 0.5 volts and the other feature was essentially where is it, the band gap. So, you can see that there is more information gain with band gap greater than 2, and what I encourage you to do is to also look at other features. So far we have only looked at these particular features, one the feature number 1 band gap greater than 2, and then we have looked at over potential less than 0.5, which is feature number 4, and out of these 2 different features we found that the former feature, right, this one is certainly better than the over potential feature, right, at least for the parent node. It is possible that this particular feature can become important in the lower nodes, right. So, we have just split the parent node and you have to keep on doing this in recursive binary splitting as you get to lower and lower nodes, but of course you can see how difficult it is to do this manually. So, this brings me to the end of this particular lecture. In today's lecture we spent a lot of time, effort and energy into seeing how one can manually design a decision stump for a problem in which you have to categorize a material as being a good or a bad material for a photoelectrocatalyst application. I hope that this has given enough intuition into the working of a decision tree. It is, although it is one of the most interpretable machine learning models, you can see that manually doing this by hand is certainly not an easy task, and this is why we need to code on computers, and we need, as core engineers, we need to develop the capabilities to get computers to do these kind of problems in an automated manner for us, right. So, I encourage you to work further through this example, keep on splitting the tree and then also implement it on a computer through Python and see that you get the same answer for a given training data set. So I hope you enjoyed this lecture. Thank you for joining today, and I look forward to seeing you next time.